Okay, testing 1, 2, 3, 4, 4, 3, 2, 1. This is a test 1, 2, 3, 4.
Talk better without thinking. 9.1, tape number 4. Collins talking. DOI through touchdown. Command module, monitor LEM DOI burn. Well, there isn't any monitoring to do other than just confirming that they did it on time and that it was nominal, which it was. Auto maneuver to sextant track, I did that, and lo and behold, the LEM was in the sextant, and I say again, this is a good exercise between DOI and PDI. It gives you an opportunity to make sextant marks and to make VHF marks and to see those marks incorporated into the state vector, and it's a good end-to-end test of the whole system. Misfin acquisition was no problem. Optics track, ease of tracking LEM. The LEM was easy to track. Auto optics worked well, and the optics drive was extremely smooth, and using resolved and low speed, it was easy to take accurate marks on the LEM. The LEM, of course, got smaller and smaller, and out at about 100 miles, it became quite difficult to see the LEM through the sextant. The LEM would appear to be just a tiny little dot of light, which was easily confused with many other little dots of light on the optics. And one trick that you can use is switch from auto to manual and slew the optics up and down and left and right. And all the other little dots that are associated with the background, the surface, will remain fixed, and the LEM will then move across them, and you can pick out which little dot is a LEM by the fact that the LEM has motion relative to the background. This technique works okay for another few miles. I don't know how long I could have kept the LEM in sight. I lost it right prior to PDI when I switched from P20 to POO. My procedures called for me to do this, and in the simulator it worked quite well. However, in the real world, at the instant at which I called POO, I went verb 37, enter, 00, enter. Of course, that ceased the P20 rate drive. And despite the fact that I was prepared for it and was looking through the sextant, at the instant the computer went to POO and the rate drive stopped, the LEM just flat disappeared from view. It just took off for parts unknown at a great rate of speed, disappeared to the 6 o'clock position in the sextant at an extremely rapid rate. It was impossible for me to bring it back, and I never saw the LEM again throughout the descent or on the surface or during the ascent until after insertion. Okay, getting back to the checklist here. Voice conference relay, we didn't use the relay mode at all, although I had little stickers made for panel 10 which showed the position of each switch, and I think that's probably a good scheme, because if you want the relay mode, you want it in a hurry and you don't want to pull a checklist out, so I'd recommend that. CSM backup pad, nothing to say about that. I, of course, used P76 to inform my computer that the LEM had made the burn. Monitoring LEM phasing, I think that's probably a carryover from F-Flight. We didn't have a phasing burn. Sextant marks, again, I've covered those. SPS setup, I did, for all burns, I did go into P40 or P41 as appropriate, and I went in those programs, or in P40, I went to the point of turning on the gimbal motors. stopped short. I never turned on any gimbal motors, but I was always, I felt able to light the motor within probably a matter of a few seconds after being informed that the LEM had not made the burn. When the LEM, during, let's see, this is just DOI through touchdown. Okay, after I went to poo, then I lost the LEM. This was a couple of minutes before PDI ignition. I just went ahead and just open loop. I followed my attitude timeline in hopes that I could see the LEM again. I did my pitch down maneuver that the flight plan called for. I did that as a Verb 49 maneuver, and it worked fine in that I had a good unobstructed view of the lunar surface, including the landing area and all that, but again, I never saw the LEM. So for future flights, I don't really know what to recommend. At the beginning of PDI on this flight, the LEM was 120 miles in front of the command module, and at touchdown, it was like 200 miles behind the command module. So the geometry is changing extremely rapidly, and there's no automatic program in the computer for helping you track. You have to abandon P20 prior to PDI, and I don't really have any helpful suggestions. The only thing I can say is just be aware of the fact that when P20 is terminated, very abruptly the LEM is going to depart the sextant field of view. And if you're all poised and are in resolve, medium speed, and switch from auto to manual at the instant the computer switches from 20 to poo, there's a faint chance that you might be able to track the LEM during PDI manually and during the descent. I tried to do this not because there was any real requirement to do so, but just because I felt that it would be a good initial condition for an abort if I were able to see the LEM in the sextant. But I was not able, and I don't have any real good suggestions for how you might do that on subsequent flights. After the LEM landed, I set the surface flag.
No reflectivity to speak of off the LEM, huh?
No, there was no evidence ever of any flash of specular light or anything like that ever off the LEM. The LEM at distances of 100 miles or so is just another little teeny-tiny little light-colored little bug that could be, a dust particle or anything like that, indistinguishable from little background surface. And the surface is pockmarked with little irregularities, light spots, dark spots, and of course P20 is driving so as to hold that surface background constant relatively, and at those distances you can't tell. You just can't pick the LEM out. You can't look in the sextant and say, there's the LEM. All you see is a bunch of LEMs, 15, 20, 30 LEMs. And the only way you can tell which is the real one, like I say, is to go to manual and drive that LEM up and down and left and right, and then you'll see one of these tiny little particles moving with respect to the others. But no reflected light, no nothing. It's beyond about 100 miles, it's very difficult. That finishes section 9 for me. Over to the LEM.
We'll go ahead with section 9.2 on the lunar module. Let's see. Yeah, it seemed as though it was, well, in the timeline, it was 20 minutes, 40 minutes before DOI that we were scheduled to begin the P-52, and we were just about on maybe 2 minutes behind that, I think, when we completed looking at the radar and VHF ranging and designated the radar down so that we could do the P-52. I think you discussed a little bit about that.
Yeah.
before, and we voiced our concern about the larger than anticipated torquing angles.
I don't think we had any difficulties with the DOI prep. At DOI ignition, which was our first dips maneuver, I could not hear the engine ignite, couldn't feel it ignite, and I wasn't, the only way I was sure that it had in fact ignited was looking at chamber pressure and the accelerometer.
Yeah.
So very low acceleration
Accelerometer
level
wasn't
while
much
you're
either.
10%. It's off zero.
Mm.
And
Really?
What's 10%?
Yeah.
Just doesn't put out very
I
much.
would think it would, you know, after 0 G, it'd throw you against your straps one way or the other and be very apparent. Not so.
now we're pulled down
Uh-huh.
into the floor with the restraint
Mhm.
already, and the
Mhm.
difference between that
Yeah.
and the 10% throttle acceleration was not detectable to me.
Yeah.
However, at 15 seconds when we went to 40%, it definitely was.
On the restraints, I found that instead of being pulled straight down, the general tendency was to be pulled forward and outboard. So much so that, now this might have been a suit problem, but my right foot around the instep was taking a good bit of this load being pulled down to the floor, and the boot was a little bit tight, not the boot, but the suit itself. That wore off well prior to power descent, or at least it got obscured from my mind. But that was aggravated somewhat by the restraints pulling down and forward.
I guess I noticed that last. I had expected a good bit of lateral shifting due to reports of previous flights, but I didn't think it was
Well,
distracting at all.
I was able to lean over and make entries on the data card without pulling it down. But as you can see, when you do make entries on them, why you make them sideways.
The cutoff was a guided cutoff, and I'll talk about the residuals.
I've got the values that we null to, unless we did in fact cut off with 1/10. You recall that? These are the ones that
we did
null to.
We did null. Yeah. I don't recall the
Yeah, we burned both X and Z, and I'm sure they weren't in excess of 4/10. But the number you remember, something like that.
it was less than 1 foot per second, but I don't recall the tenths. It's probably worth noting that the flight plan at this point in time does not adequately reflect the requirements of the flight. I think the DOI rule in the flight plan says trim VX residuals,
So it's a checklist.
which isn't right. You can't do this flight doing it that way anymore. This was a result of that orbital change that was put in, and paperwork and so on just couldn't keep up with those last minute changes. But again, it shows that last minute changes are always dangerous. you could follow the flight plan here and might follow the procedure. Do you recall the noun 80 or verb 82 values? 9.5, I think, was parallel.
Well, we're supposed pre-burn noun 42 was 57.2 and 8.5, and we had 57.2 and 9.1 after the maneuver.
I guess we can't account for that.
No, the noun 86 that we got out of the thrust program also differed from what the ground gave us in the pad, primarily in the Z component that's loaded into the AGS. The pad value was 9.0 and the computer came up with 9.5. And of course, as soon as thrust is sensed by the AGS, why this coordinate frame that you load them in is frozen inertially. And if there are any discrepancies in the freezing of this, why you will get a slight different burn direction required out of the two guidance systems, and I think that explains the larger AGS residual in the Z direction of minus 7/10. I think we'd have to have the guidance people verify that all of these, or at least that the difference in noun 86 tended toward producing that error in that direction.
We had a good manual radar acquisition and data from the radar. Agreed well with the VHF ranging information.
Again, we had P20 in the background, but we didn't use it. This was a manual lock-on, right?
Right. And the radar was depowered. To cool during the DOI to PDI phase. And these next sections in here are left over from F again, so I assume that I want to talk about those. They don't apply to our flight. The next item of significance that isn't covered in the debriefing guide is the platform drift check, which was a P-52 done against the sun. That procedure seemed to work as we had planned, but the variation in the data was somewhat larger than I would have guessed. Do you have those numbers?
Yeah, the technique that we used was to compare what the computer thought the middle gimbal or the inner gimbal angle was to point the rear detent at the sun. And we'd compare that with what the actual middle gimbal was. And we did this in, you did this in Ping's Pulse?
In Ping's Pulse.
And the way that we found to work out best was for Neil to tell me when, in the background, we'd have the auto maneuver display 5018 in P52. I would call up on top of that verb 6, noun 20 or 22. And I'd have noun 20 up, and as soon as Neil would say mark, I'd hit enter, record noun 20, and now the desire is to find out exactly what the computed value is at as close a time period. So what I would do is hit the enter on the noun 20, visually recall what those numbers are, not write them down, but hit key release, which put me back to 5018, and a proceed on that would recompute the numbers for maneuver. As soon as I would do that, those numbers would be frozen, and the desired gimbal angles would be loaded in noun 22, and then it was just a question of my calling them up, and they should not change from the point that I hit proceed. So I would say that from the time I would hit enter to record the gimbal angle that we had until it was recomputed as a desired one did not exceed 3 seconds. And of course we had pretty low rates. So I think that the comparison didn't suffer any from a lack of proper procedure. We did find that the numbers were a little larger than we thought they would be. We had it worked out with the ground how we'd arrange the signs on the differences, so we'd subtract noun 22 from noun 20, and the first one was 0.19, second one 0.16, and the third one 0.11. The go-no-go value was 0.25. So we're a little closer to this than we had hoped to be. You want to say something about the adequacy of simulator training for that?
Well, the simulator is able to correctly reproduce the control modes that are required to fly. It's an unusual control mode, whereas you fly to and pitch and fly from and yaw, while flying at AOT and depend on the other crew member to assure you that your roll gimbal angle is staying at a reasonable value. The simulator was never able to accurately simulate what you would see through the sun, and we especially set up the AOT on the GNC roof to look at what the actual view would appear to be. And in addition, on the way to the moon in the sextant, we looked at the sun with our telescope, looked at the CSM telescope with the sun filter on to get used to what the filtered view of the sun would look like in the optics, and it's somewhat different in the sextant than the AOT in color and general appearance. I can't account for that, but it is different. I thought the numbers ought to be closer than, both closer to zero if we didn't have any platform drift, or closer together in either case, but we had quite a spread there, so I'm not sure that the check in general is really as good yet as the check should be. In other words, our variation was 8 hundredths of a degree between our various measurements, and the limit on the go, no-go is 25 hundredths. So we were essentially using up a third of our margin just in variation between our marks, and that's not really a good enough procedure for this important a check on the platform. It is and was a go, no-go for the PDI. So I think that needs additional work prior to the next flight. There are some alternative methods of understanding platform drift, which we just did not have time to implement. Perhaps the next flights will be able to look at some of these alternatives and decide on even a better method than the sun checker.
Might backtrack a little bit, return the propellant quantity on before DOI, and I believe the quantity light came on at that point, which we were briefed to expect as a possibility, and just recycling the switch off and back on again would then extinguish the light. The values that we saw, I think, in fuel were about 94, 95, which is what we generally see in the simulator. The oxidizer value, I think, as I recall, was somewhat lower than that. They weren't the simulator values of 95 and 95. And I don't believe that there was sufficient time during DOI for these to completely settle down. They did go up closer to maximum numbers of 94, something like that. I don't recall the exact values. But anyway, they weren't dancing around the way we might have been led to expect them to do.
The pre-PDI attitude prevented good S-band high gain contact, and we had continual communications difficulty in this area, and finally yawed the spacecraft right between 10 and 15 degrees to give the high gain antenna more margin. This seemed to enable a satisfactory high bit rate condition, but it did degrade our ability to observe the surface through the LPD and make down and cross range position checks. I don't think that our altitude checks were significantly degraded.
I can't explain why we did have some dropouts there. The angles, 220 and pitch and yaw 30 are not ones that would lead you to believe would give you trouble as far as interferences from LEM structure. It seemed to me the initial lock-on was not bad. There was a certain rain dance you had to go through each time you'd come around to acquire lock-on, and each time you'd have LOS. We'd usually be on the omnis, and of course there's a choice of forward or aft, and then you'd want to switch to slew and slew in the proper values for the steerable. And of course, before LOS on the other side, the ground would like you to not break lock in the slew mode, because in some cases the antenna would then drive into the stops. So you, approaching LOS, you'd switch to maybe aft omni, and then you'd slew in some new numbers, we make use of 90 and 0, pitch 90 and yaw 0 to keep the antenna away from the stops. And once you drive it to those values, then you'd have to set in new numbers. And coming around the other side, you'd maybe switch from aft to forward to pick up the ground, and once you'd pick them up, you'd switch over to slew, and you might have the right values in, or you might have to tweak them up. In any event, the initial contact would be made on one antenna, and then after you establish contact, you'd have to take the chance of breaking it to then switch over to the high gain. Occasionally, we got the jump on them a little bit because the ground was talking to the command module. We saw that we had signal strength, so I'd go ahead and try and lock on the S-band. It is a rather involved process that you have to go through. I didn't find that if you left the antenna without an auto lock-on signal, and it would, say, have a tendency to drive to the stops, at least from the indication, it didn't seem to be moving there so rapidly that you couldn't, within several seconds, if you knew what you were doing, stop it from where it was going and prevent it from hitting the stops.
Doesn't mention it here, but I think we ought to just cover the altitude checks. You have that graph there.
Yeah, we had two methods of computing altitude, one based on relative motion from the CSM and the other based on angular rate track of objects observed on the ground. We superimposed the two of them on one graph and rearranged the graph a little bit in some rather last-minute data shuffling to give us something that the two of us could work on at the same time, and to give an indication of what, to either one of us, what the altitude and its time history appeared to be. With the COM difficulties that we were experiencing and trying to verify that we had a good lock-on at this point, I had the opportunity to get only about 2 or 3 range rate marks. They appeared to give us a paraloon altitude of very close to 50,000 feet, as far as I could interpolate them on a chart. I think there's one here at 42 minutes, which required an interpolation, and the range rate was indicative of an altitude slightly above 50,000.
Now those measurements give you altitude below the command module,
That's
essentially.
right. And of course, if there are some modifications of the command module's orbit from the nominal pre-flight orbit that you expect, the numbers have to either be updated or you have to accept that error.
The measurements against the ground, of course, were indicative of altitude directly above the ground. And
I think the main purpose of the radar here was to confirm that we're in the same ballpark, that we're talking about the same kind of an orbit. And I think once you do this once or twice, then it's adequate to go on with the more true altitude measuring device, which is from the ground.
the ground measurements against the ground were very consistent, but they indicate if they made a horizontal line, it would indicate they consistently told you that you were going to hit a particular paraloon, in this case 50,000 feet in the middle of the chart. They didn't say that. They were very consistent, but they came down a slope like this, which which said finally that our paraloon was going to be 51,000 feet. It steadied out at about 54,000 feet here at the bottom, and then our last point was 51,000 feet. But this indicates that either the ground was sloping, and it was in fact about 10,000 feet lower than the landing site where we started, which is not consistent with the A1 measurement that we made, or that the line of apsides was shifted a little bit, so actually paraloon was coming a little bit before PDI. So we were actually reaching paraloon a little bit before PDI, which would tend to slope the curve that way. In any case, this was all very encouraging that we were in fact going to hit the guidance box insofar as the altitude was concerned, from both measurements, the radar measurements and the ground measurements. But I was quite encouraged that these measurements made with the stopwatch were in fact consistent.
Well, when you're able to smooth the numbers and plot a reasonable number of them, your accuracy can increase considerably. I think the pre-flight estimates were something on the order of 6,000 foot capability, which I think we demonstrated a good bit better than that.
Our downrange position appeared to be good at the -3 and -1 minute point. The ignition point I did not accurately catch because I was watching the engine performance, but it appeared to be reasonably certainly in the right ballpark. Our cross-range position was difficult to tell accurately because of the skewed yaw attitude that we were obliged to maintain for comm. However, the downrange position marks after ignition indicated that we were long. Each one that was made indicated that we were 2 or 3 seconds long in range, and the fact that throttle up essentially came on time rather than being delayed indicated that the computer in fact was a little bit confused in what our downrange position was. Had it known what it was, it would have throttled down later based on engine performance so that we would still hit the right place if in fact it knew it was downrange by a couple of seconds. Then it would be late throttling down so that it would brake more at a higher throttle level prior to the pitch up. Landmark visibility was very good. We had no difficulty determining our position throughout all the face down phase of powered descent, and correlating that with known positions based on the Apollo 10 pictures was very easy and very useful.
As I recall, and this is why I kind of like to have those tapes, there was a certain amount of manual tracking being done during this time with the S-band antenna. During the initial parts of powered descent, the auto track did not appear to maintain the highest signal strength. It dropped down to around 3.7, and the ground wanted reacquisition, so I tweaked it up manually. I got the impression that it was not completely impossible to conduct a manual track throughout powered descent. You'd not be able to do very much else beside that. I think it would be possible to do if you had sets of predetermined values that you could set in case you ever did lose completely. We did have a S-band pitch and yaw angles immediately following the yaw maneuver, and those that were required at about 3,000 feet. After the yaw, the S-band appeared to have a little bit better communications. It was just about at the yaw around maneuver when we, well, I guess trajectory monitoring from the disky up to that point agreed very closely, especially in H dot and VI, with the values we had on the chart. The altitude values were, maybe off by something approaching 500 feet, but again, they were, quite close. It was almost immediately after yaw around that, as I recall, the altitude light went out, indicating that we had landing radar acquisition and lock-on. And what do you recall it being? 2,300 feet, something like that?
26 or 700, I believe, is the number
Minus.
I remember. I think it was plus 26 or 27. The yaw round was slow. We had inadvertently left the rate switch in 5 rather than 25. And I was yawing at only a couple degrees per second as opposed to the 5 to 7 that we'd planned. And the computer would not hold this rate, say 1 to 2 degrees a second. It was jumping up to 3 and back to actually changing the sign and stopping the roll rate. And it was then that I realized that clearly we weren't rolling as fast as we needed to be, and I noted that we were on the wrong scale switch so I went to 25 and put in a 5 degree per second command, and it went right around. But this delayed us somewhat, and consequently we were at a slightly lower altitude at the completion of the yaw round than we had expected to be. So we were probably down to the area of 39 or 40,000 feet at the time when we had radar lockup, as opposed to about 41,000 that we expected to be at 41.5.
There are no discrepancies noted in any of the systems that were checked throughout the first 4 minutes. The RCS was surprisingly high in its quantity indications. The supercritical did tend to rise a little bit after ignition and then started back down again. I don't recall the maximum value that it reached. I guess the first indications we had of anything going wrong were probably around 5 minutes or something. When they first started getting program alarm activities.
Probably ought to say that we did have one program alarm prior to this, sometime prior to ignition, that had the radar in the wrong spot. Remember that? We had a 500 series alarm. In any case, as I remember, we had a 500 series alarm that said the radar was out of position, which I don't have any way of accounting for that. Certainly the switches were in the right position. They hadn't been changed since pre-flight, pre-launch. But we did in fact, go to the descent position on the antenna and leave it there for half a minute or so, and then go back to auto and cleared the alarm. After the 5 minute into descent, we started getting a series of program alarms, generally of the series that indicated the computer was being overloaded. Normally in this time period, that is from P64 onward, we'd normally be evaluating the landing site and checking our position and starting LPD activity. However, the concern here was not with what was the landing area we were going into, but rather could we continue at all. And consequently, our attention was directed toward clearing the program alarms, keeping the machine flying, and assuring ourselves that control was adequate to continue without requiring an abort. And most of the attention was directed inside the cockpit during this time period, and in my view, this accounts for our inability to study the landing site and final landing location during final descent. It wasn't until we got below 2,000 feet that we were actually able to look out and view the landing area.
Okay, I see something here that answers a question we had before about the AG's residuals on DOI. They were 1/10 before nulling, and we nulled them to 0. The X was minus 0.1, Y minus 0.4, Z minus 0.1, and we nulled X and Z to 0.
Good.
And in looking at the transcripts, we did have considerable loss of lock approaching PDI. And we did have to reacquire manually several times. And it looked like we had some oscillations in the yaw angle on the antenna. And the alarm that we had was 500, and we went to descent 1 and proceeded in the computer, and then went back to auto again on the landing radar switch. And as this is prior to ignition again, and the ground recommended we yaw right 10 degrees. The rendezvous radar was on, not through the computer, through its own auto track.
We did not have the radar data feeding to the computer in the LGC position, but apparently even if you have it in auto track, why there's some requirement on the computer's time to this is the way we've been doing it in all simulations. It was our agreed on method. We were in slew. Yeah, we were, prior to this time, we'd been in auto track until such time as we started to lose lock in the pitch over, and then we went to slew. that right?
Talking about the program alarms during descent. We'd passed the point of having the rendezvous radar in auto. We'd switched it over to slew at that point. Just left it there.
We were in slew with the circuit breakers in. The radar was turned on, but it was in slew.
Well, I think we could identify that maybe.
In the early phases of P64, I did find time to go out of auto control and into manual and check the manual control in both pitch and yaw, and found its response to be satisfactory, and then zeroed the air needles and went back into auto. Continued the descent in auto at that point. We did proceed on the flashing 64 and obtained LPD, but LPD availability, but we did not use it again because we really weren't looking outside the cockpit during this phase. As we approached the 1,500-foot point and the program alarm seemed to be settling down and we committed to continue, we could see the landing area and the point at which the LPD was pointing, which was indicating we were landing just short of quite a large blocky rim crater surrounded with a large boulder field with very large rocks over a high percentage of the surface in the area. And I initially felt that might be a good landing area if we could stop short of that crater and find a suitable place, since it would have a lot of scientific value to be in that area close to this large crater. Upon continuing to monitor LPD with time, it was obvious that I would not be able to stop sufficiently short of that crater to find a safe landing area, and as soon as we determined that, we went into manual, and I pitched the vehicle over to approximately zero pitch and continued, and I think I was in the 20 to 30 foot per second horizontal velocity region here, over the top of the crater and across the boulder field, and then proceeded to look for a satisfactory landing area. And the one chosen was a relatively smooth area between some sizable craters and a ray type boulder field. At about 100 feet, or a little below 100 feet, I first noticed that we were in fact disturbing the dust on the surface, and we were beginning to get a transparent sheet of moving dust, which obscured the visibility a little bit. As we got lower, this visibility degradation continued to increase, and don't think that the altitude determination was severely hurt by this blowing dust, but the thing that was confusing to me was the fact that it was hard to pick out what your lateral and downrange velocities were, and this because you were seeing a lot of moving dust, and you had to look through that and pick up the stationary rocks and base your translational velocity decisions on that. And I found that to be quite difficult, more difficult than I thought it would be, and I spent more attention trying to arrest translational velocities than I thought would be necessary. As we got below 30 feet or so, and I had selected the final touchdown area, for some reason that I can't be sure, we started to pick up a left translational velocity and a rearward velocity, and that's a thing that I certainly didn't want to do, because you don't like to be going backwards and be unable to see where you're going. So I arrested the backward rate with some possibly spastic control motions, but was unable to stop the left translational rate. And as we approached the ground, I still had a left translational rate, and I was reluctant to shut the engine off while I still had that rate, and I was also reluctant to slow down my descent rate any more than it was, or stop it, because we were essentially close to running out of fuel, or we're hitting our abort limit. And so we continued right to touchdown in a slight left translation. The touchdown itself, I couldn't precisely tell. The buzz called lunar contact. I never saw the lunar contact lights.
I call contact light.
And I'm sure you did, but I didn't hear it, I didn't see it. I heard you say something about contact, and I was spring-loaded to the stop engine position there, but I really don't know whether we had actually touched prior to contact, or whether the engine off signal was before contact. In any case, the engine shutdown was not very high above the surface. It was quite close. And the touchdown itself was relatively smooth. There was no tendency toward tipping over that I could tell. That it just settled down like a helicopter onto the ground and landed.
We had a little, what I see here, right drift, and then I guess just before touchdown we were drifting left, huh?
I think I was probably over-controlling a little bit in this lateral. I was confused somewhat by the fact that I couldn't really determine what my lateral velocities were as closely as I would like to, due to the dust obscuration of the surface. I could see rocks and craters through this blowing dust. I had picked it out earlier at a higher altitude. It was my intention to try to pick out the surface spot that I was going to land in at above 100 feet, and pick out an area just beyond it that I could keep my eyes on all the way down through the descent and final touchdown, so that I wouldn't, in fact, be looking at the place I was going to land. I'd be looking at a place just in front of it. And that worked pretty well, but again, I was surprised that I had as much trouble as I did in determining translational velocities and being able to control them. I don't think I did a very good job of flying the vehicle smoothly in that time period. I was a little bit erratic, I think.
I was feeding data to him all the time. I don't know what he was doing with it. But that was raw computer data. Appeared to be pretty
good.
Darn close.
Yeah, the computer data seemed to be pretty good information, and I would say that my visual perception of both altitude and altitude rate was not as good as I thought it was going to be. In other words, I was a little bit more dependent on the information. I think I probably could have made a satisfactory determination of altitude and altitude rate just by eye alone, but it wasn't as good as I thought it was going to be, and I think that it's not nearly so good as it is here on Earth, let's say, flying with no big dust plume.
I got the impression by just glimpsing out that this was in the area of seeing the shadow the first time when I mentioned that. Mm-hmm. Shortly after that, it seemed to me that the horizon out there tended to be obscured by a tan haze. That may have been just an impression. Now, looking down at maybe 45 degrees, the velocity of what was being kicked up seemed to be, not velocity, but the depth of it seemed to be fairly narrow. In other words, it was scooting along the surface. But since particles were being picked up and moved along the surface, you could see little rocks or little protuberances coming through this, so you knew that it was solid there. You got the distinct impression of that. It wasn't obscured to that point. But it did tend to mask out your ability to detect motion, because there was so much motion of things moving out. You had to sort this out as to where it was coming from. There were these few little islands in here that were stationary, and if you could sort that out and fix on those, then you could tend to get the impression of being stationary with respect. But it was quite difficult to do.
That's right. It's
nothing
a little
like
bit like
that in training.
a little bit like landing an airplane when there's a real thin layer of ground fog that you're coming through, and you can see things, through the fog. Except all this stuff was moving out all this fog was moving at a great rate, which was a little bit confusing.
And I would think that it would be natural that looking out the left window and seeing this moving this way, you'd get the impression of moving to the right, and you'd counteract it by going to the left, which is how we touched down.
Since we were moving left, we were yawed slightly to the left, so I could get a good view of where we were going. I think it was 13 degrees left, and consequently the shadow was not visible to me. It was behind the panel, but Buzz could see it. Then I saw it in the final phases of descent. I saw the shadow come in to view, and it was a very good silhouette picture of the limb at the time I saw it, probably a couple 100 feet out in front of the limb on the surface.
Well,
it's clearly a useful tool, but I just didn't get to observe it very long.
Here's an entry, 46 seconds, 300 feet. 4 seconds after the next minute, watch your shadow. And at 16 seconds, 220 feet. So I'd estimate that I called out that shadow business at around 260 feet. And it was certainly plenty large at that point. And looking back on it, I would have said that at 260 feet, that shadow would have been way the hell and gone out there, but it wasn't. It was a good-sized vehicle. I could tell that we had gear down and that we had an ascent stage and a descent stage, and it was, of course, illuminated around it with the zero-phase sun. So there was a brightness in the vicinity, but it was readily identifiable, and had I looked out sooner, I'm sure I could have seen something identified as a shadow at 400 feet maybe higher, I don't know. But anyway, at this altitude, it was usable. Just how you sort that into all the rest of the things that you're looking at, since the ground is moving, why, it might be of some aid. But of course you have to have it out your window. Well, that's why I said before, I had the impression of further away from us there being dust up, because I got the impression that it obscured the horizon. I wasn't too interested in that except for maybe some level indications. Well, it seemed to be moving right along the surface, but since it gave this impression of being up, somewhere along there it must have billowed up, but it wasn't clear where it was doing this. Coffee time? Well, how about the LPD?
With respect to the LPD operation during descent, the LPD was not used until we were below 2,500 feet, and it was followed for some number of comp cycles subsequent to that time, and the landing point moved downrange with time, as evidenced by successive LPD readings. Guess we can go.
Do you recall when you proceeded?
It was very shortly after initially going into P64.
Because here we got P64 at 41 minutes, 35 seconds. And you went manual attitude control.
I can't say
well,
whether that was before or after proceeding.
Because it wasn't too long after that. Let's see. 41:35 P64, 42:05 manual attitude control's good, and 42:17 program alarm. What I'm wondering is, did the proceed have anything to do with maybe generating some more activity which would cause a program alarm? We weren't in 1668 at that point.
I have no recollection of that area. Okay, section 10, lunar surface. The post-landing checklist went as planned, and venting was initiated in the aux tank almost immediately, even before the point on the timeline at which venting is called out.
Yeah, it was a minute and a half at the most before we
we ran the aux pressure down to 40 to 50 psi range, and then opened a fuel vent and drove it down the same, closed it off, after which time Houston became concerned with the tank pressures and asked us to reopen it again, although at the time we were reading still relatively low tank pressures. I think the aux built up slightly over 50 at the time, but they were apparently reading a higher value, and I assume that perhaps they had an error in their signal from that tank pressure. In any case, we opened both tanks after that and let them bleed down to about 15 psi, which was probably the stable condition of vapor pressure in the tank at that point.
Now,
Going back to this before touchdown protocol, one thing here, before you got the production test, you feel you had a good feel for the size of the rocks you're looking at, what kind of questions you might look to look at, how it takes place in the way, and that kind of spot.
I wouldn't say that I could guess that maybe they were 1 foot or 2 feet in size, but in general, could tell the general altitude and size of craters and rocks, and I could, in fact, pick out a place from several hundred feet that seemed to be adequate for a touchdown. Yeah, but I think I had in the back of my mind at that point a fairly good confidence in the fact that the 200 to 300 foot altitudes that we were getting out of the computer at that point were in fact right. Everything seemed to add up correctly at that point to indicate that that's where in fact we were. Which you sort of need that as a baseline before you can look at the ground and say, yeah, well, that looks like a good spot. You have to assume something about where you are. And the cards stacked up to indicate at that point that we did, in fact, know what our altitude was, roughly. Well, I wouldn't go so far as to say that. Would I put myself in the same spot without that confidence? I think I'd continue and feel like I know where I was, but I don't think that now, looking back, I don't feel like I'd be as confident at that point as I thought I would be. In other words, pre-flight, I thought I'd know pretty well what my altitude and altitude rate were. Now, I don't feel I would know it quite as well as I would have thought.
after touchdown, we got a go for T1, and then we proceeded to enter program 68 and recorded the latitude and longitude and altitude. Proceeded out of that, reset the stop button, and entered P12 for T2. Now at this point, I think that a little shuffling in the data cards might prevent someone from making the same error that I did in loading the TIG for ascent. On the data card, we've got the PDI pad, which is referred to somewhat during descent, and then the PDI aborts are on there, and to the right we have the no PDI plus 12 abort. I think that no PDI plus 12 abort would be better placed on the back maybe of this altitude card, because once you ignite, you're through with that no PDI plus 12 abort, and you ought to get it the heck out of there. In its place, I think the T2 abort pad should be on the data card, because what I did was, when I started to load P12 with noun 33, the TIG, for this T2 abort, which is PDI plus 23, I loaded the TIG for the no PDI plus 12 abort, and the ground caught me on it and said, you loaded R2 wrong. And instead of loading 102.54.29, I loaded 102.44.27. Now the two are pretty close, and they both say noun, well, they both say TIG, noun 33. So I think if we can get that one abort, no PDI plus 12 abort out of there, and put the other one in its place, it'll save anyone from coming up with the same sort of thing.
Well, just stop.
Okay, you talked about the oxidizer vent that we had. Well, why don't you say again the sequencing of oxidizer and then fuel down to PSI and then closing them.
The oxidizer was vented down to about 40 or 50 psi. Just took only a couple minutes, several minutes. It was a little faster than I expected it to be. Then we opened the fuel vent, dropped it down to even lower value than that, shut the valves, and the ground became concerned with an overpressure and oxidizer, although it apparently climbed only up to about 55 or 60 psi. We opened both valves, and they remained open until the pressure stabilized at a steady state condition of about 15 psi, I would guess. And they stayed that way for quite a while, and then we shut both valves.
And let's see, we got the things back to mode control back to attitude hold and ags to off. And then cycled the Parker valves again, and after having seen the erroneous talkback indications, I was expecting that when I put the feeds to close that they would indicate open momentarily, and also when the cross feed was cycled again to close, that its talkback would give a gray indication. Turned the camera off and proceeded with switch configuration. Cycling the CW circuit breaker did in fact turn off the descent reg warning light. We read out the sine and cosine out of the ags, and I'm sure they copied that down. Went immediately into recording the gyro, the ags gyro coefficients, which let me just, I'm sure that these were the same numbers that we finished up with, but it might be a good time just to check. Yeah, what I'm doing is verifying that the ags gyro coefficients are the same that we saw on the surface before the calibration as the ones we saw after the calibration and activation, and they are the same, minus 3033 plus 406 minus 3037. Then went to cabin on the regulators and took helmets and gloves off at this point, right?
Right.
And started in with the initial gravity alignment. And see, you've got these numbers recorded down here. I don't have the first down 4 that we got. Remember the one that we did a recycle on?
Mm-hmm.
I didn't record that one, but it was fairly large, but I've seen so many of them in simulations I just can't recall what that number was.
Sure, that's recorded on the ground.
After the recycle, it was 401. We asked them about recycling, and they said affirmative. We've got a star angle difference, or angle difference of 3015. And the torquing angles, which showed a fairly good change. Let's see, I guess the pitch one is the one you're concerned with. That's about the y-axis. That was 1/10. And I don't know whether the sign of that agrees at all with the approximate 1/10 that we got in the sun check. That'd be interesting to look at. We then proceeded let me see, we did not torque those angles. The idea was to get a gravity direction and then to do a 2-star alignment and look at the drift, look at the torquing angles after the 2-star check, which would then give an indication as to what the drift had been since the last alignment. The initial gravity alignment combined with the 2-star alignment would produce then a potential new location of the landing site, which, since the ground didn't want us to incorporate in it, evidently they didn't care for that one too much. In selecting the stars, had we landed straight ahead, my intent was to use Capella and Rigel. And why don't you hold here just a second. The intent was to use Rigel in the left detent, number 6, and Capella in the right detent. The 13-degree yaw moved Capella out of the right rear detent. Rigel was in good shape there, and that's the one I used first. I then selected Navi in number 4 detent, the right rear, and that wasn't particularly satisfactory. It was quite dim, and it took a good bit longer than I had hoped to get the marks on that. Can't comment particularly on the star angle difference, other than it was a little disappointing that it was 409. Torquing angles we have recorded, and we did torque the latitude and longitude. We'll have to listen to the guidance people to just what that did to our possible touchdown point. It seemed to me when we finished that, we were just about on schedule, maybe a little bit behind, so we proceeded into the option 3, which was gravity plus 1 star. And since Rigel had been so good, I used that one again. The gravity alignment seemed to be quite consistent. The first time it did the gravity alignment on this option 3, it came up with 5 zeros. Our star angle difference on the gravity plus 1 star, which indicates an error in the gravity measurement and the star measurement, was 408. And the largest Well, no, we have the torquing angles down here on that also. The azimuth is fairly large, 0.2 degrees. We received a go for T2, or T3 I guess it is. Might want to look over some of these comments in here that we have out the window while we're getting ready for these alignments. Oh, just in the vicinity of loading these times for the T2 abort, I noticed that the mission timer wasn't working. And it was frozen, is that right? At some particular time, I don't recall what time, but it just stopped. We checked both.
No, it hadn't just stopped. It had some
yeah, it had gone to 900
900
hours.
and some hours, and couldn't correlate the minutes and the seconds with any particular previous event.
Yeah, 902:34:47. I don't know what time that relates to. Obviously, the 9-digit changed. It might have stopped, but it was static at that point. And we ran through the circuit breakers and couldn't seem to get it moving again, and ground suggested we turn it off. And then one time we turned it back on, we had all 9s, and you could change the last digit with the digit sequencer. And we turned it off for a while and got it back on again, and it worked after that. And we gave them an e-memory dump. Got a new ascent pad with a CSI pad. This is for T3. And we proceeded on with the option 3 alignment. And continuing on through the checklist, looking at switch settings and circuit breaker cards. And we found ourselves 10 minutes to go and essentially up on the checklist at the point where we had to start pressurizing the apps if we were going to launch. And we just read through the remainder of the simulated countdown and decided that there wasn't any point in sticking with that timeline any further. So we terminated the simulated countdown and went to the initial power down sequence. We had discussed among ourselves the possibility of
evaluating during this first 2 hours whether we wanted to go on with the rest period that was scheduled or to proceed with the EVA preparation. And I think we had concluded before the end of the simulated power down that we would like to go ahead with the EVA. And it was sometime in here that Neil called the ground and let them know of that.
Were two factors that we thought might influence that decision, and one was the spacecraft systems and any abnormalities that we might have that we'd want to work on. The second was our adaptation to 16G and whether we thought more time in 16G before starting the EVA would be of advantage or disadvantage to us at that point. And basically, my personal feeling was that the adaptation to 16G was very rapid and was very pleasant, easy to work in, and I thought at the time that we were ready to go right ahead into the surface work and recommended that.
Yeah, we estimated EVA at 8 o'clock. I think that was a little optimistic. I guess
About an hour
the
optimistic.
ground recognized that because they said, do you mean beginning of prep or beginning of hatch opening? And all during this time, why we could tell that Mike was kept busy each pass doing P-22s, trying to find out where we were. Okay, we want to go back and look over this again?
I've been doing that, and the only things that seem worth commenting here are observations from the window prior to the lunar surface work. And I think it's most of those comments are included in the air to ground, but just to repeat, we're in a relatively level and smooth area covered with craters, and craters varying from up to perhaps 100 feet in the near vicinity down to less than a foot, with density relatively inversely proportional to the size of the crater. The smaller there were, the more there were of them. The ground mass was very fine silt, and there were a lot of rocks of all sizes, angularities, and types in the area. Our immediate area was relatively free of large rocks. Several hundred feet to our right, there was a significant boulder field, or array of boulders, essentially, that had many large boulders greater than 1, 2, or 3 feet in size. We never were able to get over into that area to look at those rocks in detail.
Distances appear deceiving. When we looked at this fairly large boulder field off to the right, it really didn't look as though it would be too far away at all. Before we went out, of course, once we got out, we wandered about as far as it seemed appropriate. Of course, we never did come close to this particular field. What really impressed on my mind the difference in distances was after we were back in again, looking out at the flag, the television, and the experiments,
they looked as though they were just right outside the window, when in fact, on the surface, we'd moved them a reasonable distance away. So I think distance judgment is not too good on first setting down. The tendency is to think that things are a good bit closer than they actually are, which says that they were probably a good bit larger than what we might have initially estimated also.
Probably the most surprising thing to me, even though I guess we suspected a certain amount of this, was the light and color observations of the surface. The down sun area was extremely bright. It appeared to be a light tan and in color, and you could see into the washout region reasonably well. Detail was obscured somewhat by the washout, but not badly. As you proceeded back toward cross sun, brightness diminished, and the color started to fade, and it began to be more gray. As you look back as far as we could from the lamb windows, the color on the surface was actually a darker gray. I'd say not completely without color, but most of the tan had disappeared as you got back into that area, and you were looking at relatively dark gray. In the shadow, it was very dark. You could see into the shadows, but it was difficult to...
small gradations in color that were the result of very small topography changes.
Now, of course, when we actually looked at the material, particularly the silt, up close, it did in fact turn out to be sort of charcoal gray, or the color of a graded lead pencil. Now, how that kind of stuff can look light tan and very bright out in front of you, essentially like the color of this wall here, and you know it's really this color, but when you look at it, it looks like that, is still a little bit of a mystery to me.
Well, we were just the first of many to be impressed by this.
Well, you can hear that and believe it and not think too much of it, but when you're actually faced with trying to interpret that kind of color and that light reflectivity, it is amazing.
Well, they did use very dark colored material, very finely powdered, and then when they would illuminate it, it did have a gray appearance, but their gray was considerably darker gray than what we were seeing. We were seeing very brilliantly lit, and down sun it was approximating going into white, a very light gray.
Wouldn't you say it's something like the color of that wall isn't very far away from what it looked like? And yet, when you looked at it close, this is where it was. It's a very peculiar phenomenon. I think we're ready to go into surface prep, huh?
Yep.
Now, a preliminary comment has to do with the longer time that it took than our simulations. Is attributable to the fact that when you do simulations of EVA prep, you have a clean cockpit and you have all the things that you're going to use there in the cockpit with you and nothing else. On the real fact, thing you have is a lot of checklists and data and food packages and stowage places filled with odds and ends, binoculars and stopwatches and assorted things, each of which you feel obliged to evaluate as to whether its stowage position is satisfactory for EVA and whether you might want to change anything from the pre-flight plan, such as the fact that our mission timer was out and we decided we better leave one wristwatch inside in case it got damaged EVA, that we'd at least have one working watch to back up the mission timer or to use in place of the mission timer in case we never could get it going again, which is the way it appeared at that time. And all these little items took a little bit of time, a little bit of discussion, which never showed up in any of our EVA preps on the ground. And that really accounted for the better part of an hour of additional time. And our view of the EVA prep was that we weren't trying to meet a time schedule. We're just trying to do each item and do it right sequentially the way we'd learned to do it, not worry about the time. Well, the result was that there was a lot of additional time used there. I don't think that's wrong. I just think that in future planning, you're probably better off adding a little time for those kinds of things.
And no matter how many times you run through an EVA prep, to the best of the trainer's ability, he's put things in what he feels is a logical sequence. But when you're faced with doing these things, you have something in your hand and something on your mind and you want to do something with it, so you go ahead and put it where you think it's going to be, because you're going to get to that pretty soon. So there is a natural tendency to deviate somewhat from the printed sequence that you have. It's a rather complex operation, and nobody writes a checklist to tell you in the morning when you get up all the sequences you go through to put your clothes on and brush your teeth and shave and all that. And if you had one sitting there, you wouldn't follow it the same every day. You'd make small little deviations just based upon what seems appropriate at that time. It's a very difficult thing to build a checklist for.
We shouldn't imply that the EVA preparation checklist wasn't good and adequate. And we did, in fact, follow it pretty much to the letter, just the way we'd done our training exercise. That is, the hookups and where we put the equipment and all that, and the checks and so on were done precisely as per our checklist, and it was very good. And I don't have complaints about that at all. It's these other little things that you don't think about and don't consider that took more time than we thought. There was one control on the Bliss that surprised us, and I don't know if it was different from the trainers or the flight Blisses at the time we were looking at them or not, but there was a press-to-test knob of some sort that neither one of us could correctly identify as per function. And to this time right now, we're really not quite sure what it does.
There's a thumb depress button that seemed to go in somewhere as if it was relieving some pressure from something. And I can't remember ever having seen that before. It protruded out toward your back, and it looked as if it might come fairly close to riding on the back of the suit.
We both thought that we knew that the EMU very well and knew every function and how it operated, but it turned out we were wrong. There was something that we hadn't learned there, and if it had been there before, somehow it escaped us, and that took us a little time to discuss that, and we proceeded on.
Mounting the 16 millimeter camera on the two universal brackets, one on the mirror mount and the other on the crash bar, went pretty much the way we had planned it to go. The two brackets with the enlarged knobs helped out tremendously in that I was able to tighten them down to a much greater degree than I had any of the training models that we had, and it gave me much greater confidence that the cameras would stay where I placed them and that there'd be no problem with any camera banging into the window when we didn't want it to. The RCU camera brackets were difficult to tighten down. By tightening just as hard as we could, there was still a little bit of play in both of them, and I think an improvement in that knob would be quite advantageous, to be able to cinch that one down a little tighter, and perhaps the same kind of a knob that has edges that stick out so that you can get much higher torque on them would be a good thing to do.
I think all the remainder of the EVA prep went as per checklist.
Yeah, the mounting the OPSs, heaters tested out, both lights came on. Pressures regulated at very close to 3.7. And then when it came time to unstow the hoses, the pressures had dropped down to, didn't they drop down to just about zero?
Yeah, they were below
Below the
2.5 is the minimum.
Overshoes went on quite easily. We put the anti-fog on as soon as we got the kit out, instead of waiting until a little bit later. And I think that maybe there were two things that brought that about. One of them was we weren't really sure that it was going to appear later in the checklist and wanted to make sure we had that. And the other was in doing training, we wanted to avoid as many activities as we could with the PLIS on our back, because it was very uncomfortable in 1G doing any additional exercises with the PLIS on. I did find, however, that it was quite comfortable, even without the shoulder pads, to have the PLIS mounted on your back. The mass of it was not at all objectionable. It did require moving around methodically and very slowly to avoid banging into things. No getting around it. You just couldn't always tell what you might be, what the back of the PLIS or the OPS might be in contact with at any particular time.
And as was reported, we broke one circuit breaker with the PLIS, and we depressed two others, one on each side, sometime during the operation with the PLIS on the back. So that's an area that we still need to improve on to be able to have confidence that the integrity of the limb itself won't be jeopardized by the operation with the PLIS on the back. Now, depressurization.
Well, let's get to the one connector that gave us problems.
Oh yeah, let's talk about
We'd
that.
had problems with this one particular electrical connector, the one that joins the RCU to the PLIS, ever since the first time we've ever seen them.
It's about a 50-pin Bendix connector.
And it's just very difficult to get the thing positioned properly so that the 3 pins on the outside, the 3 little protuberances, will engage in the ramp so that when you then twist it, it'll cinch on in. And that must have taken at least 10 minutes. The problem was not with mine, but it was in hooking Neil's. And I can't say that there was that much difference in the many times when I tried it unsuccessfully and the one time when it did go in correctly. It appeared to be squared away each time.
This is not because we didn't understand the problem.
No.
We had trouble with that connector for 2 years or more. We'd always complained about it. It had never been redesigned, and it was usually ascribed to the fact that all the training models were old and gouged and so on. But when we looked at the flight units on our CF squared on the EMU, it turned out they were still difficult. And we accepted the fact that by being very careful with that connector, we could, in fact, connect and disconnect it satisfactorily. And we did that in the lab at the Cape. We had a little bit of difficulty with it there. When we got in flight in the surface, it was the same problem. It took us at least 10 minutes apiece to make up each of those connectors. And it's the big electric cable from the RCU to the PLIS. Attaches at the PLIS end. And it's our recommendation, I think, that it's a sufficiently serious problem that we can't afford to jeopardize the success of an EVA on that connector, and that's right now what we're betting. And it began to look like we never would get those connectors made on the surface, and we just have to improve that. Now, the depressurization sequence was one.
Calm.
We aren't to that yet, I don't think.
No. That comes before depressurization.
Okay, it doesn't show up.
Connecting up the straps went quite smoothly. The initial COM checkout on the audio panel and the various communications checks we made in the FM mode all seemed to go quite well until we started switching the PLIS modes. And for a while we ascribed some of the difficulty perhaps to the antenna being stowed, so I unstowed Neil's, and that didn't help immediately. A little later it seemed to help out, but then we got back into about the same problem, so I stowed his antenna. There didn't seem to be any particular rhyme or reason to when we did appear to have good comm and when we didn't.
I guess just suffices to say that we never did understand what was required to enable good comm while we were inside the cockpit, relaying through the PLISs. We had it part of the time and we didn't part of the time. But we tried a lot of various options and they didn't, they just weren't universally successful, but we were able to have adequate comm to enable us to continue. I think once outside, we really didn't have any appreciable comm problems at all. It seemed to work well. Now we'll get into the depressurization sequence. This was one area of flight preparation that was never completely performed on the ground. In the chamber, the plisses were left on the engine cover, and we never put them on our backs due to their weight and jeopardizing the integrity of the limb and so on in the chamber. So the comm was operated and the connections were made, but a depressurization sequence with the plisses on the backs was never completed. The times when we actually operated the pliss, it was done always in the chamber and never done with the limb systems operable. So two things were new to us. One was the fact that it took a very long time to depressurize the limb through the bacteria filter with the pliss adding gases to the cockpit environment. This was, I guess, water boiler operation or something. It was adding some cabin pressure. And the second was that we weren't familiar with how long it would take to start up the sublimator in this condition. And it seemed to take a very long time to get through this sequence of getting the cabin pressure down to the point where we could open the hatch and getting the water turned on in the pliss, and then getting the ice cake to form on the sublimator, getting the water alarm flag to clear so that we could continue. It just seemed like it took us about a half hour to get through this depress sequence. And it was one that we'd never duplicated on the ground, so in retrospect, it all seemed to work okay. It was just that we weren't used to spending all that time standing around waiting. It seemed like forever. Yeah.
Well, there's a step. Verify PGA pressure above 4.5 and decaying slowly. And it did that. It decayed slowly, and the cabin stayed at around 1 psi or about that. And we had to get that down before we could open the hatch, it appeared to me. And we were just waiting there between those steps of PGA pressure and cabin pressure coming down and opening the hatch. And we didn't really want to go and open up the overhead hatch. We'd like to only open one of them and leave the other one the way it's been. When the hatch was finally opened, why, it did take an initial tug on it, and it appeared to bend, the whole hatch. As it opened on the far side and came toward me, as soon as it broke the seal, it appeared as though I could see some small particles rushing out, and then, of course, the hatch came open and gave us a more complete vacuum. And then we went to the opening the water. Seems to me that if there is that delay to get rid of that pressure, that maybe one could go ahead and open up the water ahead of time before you actually get it down to the point where the hatch is open. Maybe that would compound the problem. Once the water window did clear, why, it seemed that the cooling was noticeable almost immediately.
Let's see, I guess the final system status was without problems, and the Egress was initiated. And I guess the most important thing here with respect to the egress through the hatch and the work on the ladder and the platform is that our simulation work in both the tank and in the airplane was a reasonably accurate simulation of the real case, and it's adequate to learn to do the job. We didn't have any big surprises in that area. The things that we'd learned about body positioning and arching the back and clearances required and one person helping and another and so on played. They worked just like that in the real case. There weren't any difficulties in movement through the hatch, stability on the porch. We made after getting onto the porch, I came back into the limb and went up around the Z27 corner. Made sure that was as expected, and it was, and we returned out to the porch, got on the ladder, discarded our duffel bag with the armrests, and OPS pallets, released the mesa without any difficulty, and descended down the ladder just as expected. The step was pretty high. The first step, 3 or 3.5 feet up to the first step. So the initial test was to see if we had any trouble getting back up on the first step, and it wasn't any difficulty. So we proceeded with the planned activities. The work required and the effort required to go up and down that ladder and in the hatch, I don't think are high enough that they need to be worried about. That is, I think going up the ladder, going through the hatch are not high workload items. They are items that require some caution and practice. Probably I had it a good bit easier than Buzz did, since he had to do it by himself. He had to go through the hatch and around the corner by himself. But
once I was with my feet and fanny out through the hatch, while Neil was in good position, as good as I was in, to help him move out by just observing the profile of the Bliss as it matched with the hatch opening.
the two-man operation there is good, because all the help that each man can give the other one is money in the bank.
I think the initial first man moving out is a little bit more difficult, because the second man has to be back behind the hatch and has to try and move it out of the way. So you had the tendency to be more over toward your side, away from the hatch, and anything that you were contacting was usually on your side, your edge of the lower part of the disky table.
There weren't any temperature effects noted in the egress or ladder. Nothing felt hot or cold or had any temperature effects at all that I was aware of.
The platform itself afforded a more than adequate position to transition from going out the hatch to on the ladder. The initial step is a little bit difficult to see when you get to the first one. At least I was glad to have you tell me about where my feet were relative to that first one, so that I didn't have to make a conscious effort to look around to the side or underneath. But I think that what I'm getting at is that operations on the platform can be carried out without concern about losing your balance or falling off. There's plenty of area up there to stand on a step and do any manipulating that might be required. And of course what I'm getting at is that there are alternate ways of bringing things up, alternate to the LEC, and I think that they do show promise of being able to bring things up over the side, straight up, versus making use of the LEC. We didn't have the opportunity to exercise those.